co-director, I'd like to welcome you all to the 14th year of the Citrus Research Exchange Seminar Series. We have hosted a remarkable lineup of technology innovators in person at Satyajit Hall and are glad to see all of you joining virtually today for the Spring 2023 series. Before we begin the talk, I want to highlight a few upcoming Citrus events. The next Citrus Research Exchange will be held next Wednesday, February 1st from 12 to 1 p.m. Pacific time for a discussion on climate change effects on hurricane risk for single-family houses in the U.S. with Dr. Markele Barbato, professor of the University of California, Davis Civil and Environmental Engineering Department, co-director of the UC Davis Climate Adaptation Research Center, and director of the Citrus Climate Initiative. Please check the Citrus webpage for registration details and further updates. For our virtual participation guidelines, before we get into the talk, please post all of your questions in the Q&A box on Zoom. You should see a Q&A icon in your Zoom toolbar. Clicking the thumbs up on a question will help bring it to the top of the Q&A window, and we promise to have a lively discussion at the end. Questions will be addressed at the end of the talk. Today we are joined by Dr. Spencer Castro. Spencer Castro is an assistant professor in the Department of Management of Complex Systems at the University of California, Merced. His research encompasses workload measurement and modeling in human-machine systems, especially within human-computer interaction, driving, automation, and data visualization and manipulation. He received his Bachelor's of Science in Science, Technology, and Society from Stanford University in 2011, and a Master's of Science in Psychology from UC Santa Cruz in 2015, and a PhD in Psychology in 2019 from the University of Utah. Castro received a National Science Foundation Predoctoral Graduate Research Fellowship, or GRFP, in 2015 to study mobile device interactions while multitasking. In 2019, he received a postdoctoral fellowship at the University of Utah to model real-time cognitive workload fluctuations in applied settings. These settings included conversations while driving and monitoring autonomous aerial vehicles. As a fellow community member of Yosemite National Park, it is my great honor to welcome Spencer Castro.
Thank you very much for that generous introduction, and always good to see a fellow Ahwahnee resident. We are far and few between. So I guess now I should move on to sharing my slides. Okay, just want to clarify that you are now seeing them.
That's right, thank you.
Okay. So today we're going to be talking about the multitasking motorist and interactions with technology. The background of multitasking comes largely from psychology and cognitive science, but with the advent of all sorts of new technologies, a lot of display-based technologies that allow us to interact in ever more ubiquitous locations, such as mobile devices, we end up with an explosion of novel types of interactions. So in order to get through some of the early work, we're going to talk briefly about the background of driving in the world, the modern definitions of levels of automation in driving, what workload is, and then how we go about applying it to different scenarios. These scenarios will include how handheld mobile device size and location may affect tasks differently when trying to do them simultaneously along with other tasks. So cell phones versus tablets and screen sizes, and what dual task cost is. We'll talk about one of our secondary task measures for getting at this concept of workload, and what workload ratings mean, and how we came to that conclusion of using this slightly, I guess, unintuitive measure. We'll talk about what we can do with it in terms of computational modeling of the responses to get at some nuances that statistical tests of averages might not be able to tell us. Then we'll apply that in some simulator and lab settings. So naturalistic conversations while driving, and then intermittent multitasking like you might do when you're texting on the road. If we have any extra time, I'll talk through some current projects which involve more applications of these methodologies. And some of those include bike navigation and decision making and route planning, etc., when evacuating from wildfire. So I'll dive right into this. We recently wrote a chapter called The Multitasking Motorist, and the chapter explains a bit about the context that we're trying to understand, which is the concurrent engagement in a secondary task that diverts attention from primary task of operating a motor vehicle. The main goal always of driving is to get to the destination, but we know that there are many other secondary goals that exist, which comprise technological interactions, conversations, fatigue and boredom. All of that involves this concept of workload. So impairments to driving can stem from interference, but they can also stem from just diverting attention away or having under arousal, not enough attention to that primary task, and then performance starts to suffer. So with that in mind, this is what a study on the road might look like. You'll see these individuals working to interact with a voice command system, which means they're probably pressing a button against a steering wheel to engage the voice activation system, speaking some sort of command in some very specific way, and then getting responses from that system. This system is to keep eyes on the road and hands on the wheel, which both were the National Highway Transportation Safety Administration has guidelines to original equipment manufacturers about how long you can take eyes off the road, how long you can take hands off the wheel. So those things were regulated, but taking your mind off the drive was not. Here we go.
Okay, Google.
Oh, watch out. Oh, it's green. No, yep, watch out.
Plane got in late, so I'm just heading over to the airport now. Oh,
Do you want to send this?
yes.
Oh my gosh, I guess that is a stop sign. Woo.
Contact Joel Cooper. Oh,
Please say a command after the beep.
Call Anna Turner.
Call Henry Burns.
No,
To call.
no.
Please say a command after.
Call Anna Turner.
Call Henry Burns.
phone, dial Amy Smith at work.
Okay, calling Del Reed.
Huh?
Okay, so in the video, you can tell that the drivers are struggling a little bit to interact with the system. The system makes errors, and those errors have to be corrected. And the interactions are not at all like naturalistic speech, where you request something, maybe ask for clarification, and are able to receive it. Technology continues to improve in that regard. This is circa 2015. So we've advanced fairly beyond this capacity. However, in a kind of Wizard of Oz style approach, where we have somebody speaking the responses to those commands through the speakers, your performance in secondary tasks and our measures of workload is still increased. So we're working with this type of framework where we have a limited capacity for attention. We can only attend to so many things in the environment at any given time. And in order to complete the task of driving, we have to scan our environment, predict potential hazards and outcomes, identify important information. So we do some sort of filtering where we can't take in all information at once, like a computer might. We have to make decisions, and then we have to execute those responses. When you divide your attention across multiple tasks, it decreases the amount of limited capacity that you have in order to maintain your situation awareness. Now, why does this framework matter? Well, one of the things that we maintain when we're maintaining our situational awareness is our understanding of how good we're doing, or our metacognitive abilities, how we're self-assessing our abilities to drive. So a AAA Foundation for Traffic Safety study found that 88.6% of respondents felt that cell phone use while driving was a very serious threat to personal safety. 45% supported a total ban, 70% supported a restriction, and then 88% of drives in a 2017 study found that, 88% of drivers during a 2017 study found that people were using their cell phones. So actual use and people believing that it's a threat is about the same number. This is important because what it comes down to is people believing that others driving on the road and interacting with other devices is dangerous. But they themselves don't have the metacognitive abilities to tell that their driving performance has been impacted. Basically, they can't tell that they're driving poorly. So at any given daylight moment, 9.7% of the public can be seen using their cell phone to talk or text while operating a motor vehicle as of 2019. So this is obviously a problem. And one of the solutions that everybody is very excited about is automation. So we have these automated systems like lane keeping assist and adaptive cruise control. But what most people don't realize is that we are kind of mostly straddling this gap between level 2 and level 3 automation, where either you are driving and the support features are engaged, but you are technically in charge of the vehicle, which means you must constantly supervise the support features. You must either steer or brake or accelerate to maintain your following distances, your lane keeping, all of those things. Some level 3 driving systems do exist where you're not driving, but you still have to monitor the systems, because when the feature requests, you must take over. So you must drive. The reason this is important is a lot of systems and companies, for example, Waymo, their goal is to eliminate the driver. However, that goal is still, I believe, potentially decades away in terms of having a system fully automated where there is no interaction, there is no steering wheel, the driver doesn't actually have to do anything, and if a crash occurs, it is the fault of the system. So in terms of level 2 features, we have steering and brake / acceleration support to the driver, like adaptive cruise control, lane centering, and then an idea for a level 3 system would be one that can successfully navigate a traffic jam on a freeway. So adaptive cruise control and lane keeping, but also monitoring for people cutting in, turn signals, construction, all of those types of things. Those features can drive the vehicle under very limited conditions and will not operate unless all required conditions are met. For example, if it's cloudy, or if it's raining, or if it's nighttime, or if there are significant number of stop lights, intersections, those systems no longer can function. So we are stuck in this SAE2, level 2 and level 3 space, especially when we are always going to have older models of vehicles on the road. We can't switch overnight to all of these semi-autonomous or autonomous vehicles that then communicate with each other and maintain their distances from one another. It will be a long time before all of the current vehicles that are being made are phased out towards these fully autonomous vehicles. So the human is important. That is the point. And because the human is important, we have to factor in what the human does. And one of the ways we factor in what the human does is workload. According to Hart and Staveland, the creators of this NASA Task Load Index, which I'll talk about in a second, workload is the perceived relationship between the amount of mental processing capability or resources and the amount required by the task. It's fairly vague definition, and they provide all of the ways that it is very complicated. So we have imposed workload, which is the workload required by the task, and that depends on objectives, so goals and criteria. For example, a lot of driving today is done as good enough. So lane keeping has some error. It doesn't have to be perfectly centered. There's error on both sides. Following distance has some error or buffers. All of these things reach a sufficient but not perfect level that is required to not hit anything. So there's also some extra wear and tear on the vehicle, depending on if you're an aggressive or a cautious driver. Fuel savings associated, where there's an optimal way of driving that saves fuel. And we'll talk a little bit about what the accuracy or the precision of fuel tank measures and what could be potentially saved in with gas saving measures. And then there's the temporal structure, so the duration and the rate of difficulty. The environment changes, so there's social environment and the physical environment itself. Physical environment meaning steep, windy, a lot of decision points, something along those lines. Social environment meaning, my example is always talking on a cell phone. The person doesn't know the context that you're driving in, so you can be driving in a completely boring straightaway with no vehicles around, or you can be in a multi-decision point traffic jam, and the person on the other end of that phone call doesn't know how that works. There are rules of politeness in conversations that impel you to answer during a certain amount of time, and therefore primary and secondary tasks can be confused. The incidental variables, for example, the system can fail. Technology tends to fail. You saw some of that in the video. Operators make errors. The environment is dynamic, and the state of the operator, which we have laws about, blood alcohol limits, fatigue. People can't, commercial drivers can't drive continuously for a certain amount of time. And then there's learner permits, etc. Some of this overlaps with operator behavior. There's a selection of strategies, operator capabilities, and commitment of resources. So you can try harder, be motivated more. There's individual differences in everybody's top end driving ability. And there are, like I said, cautious versus aggressive types. And then the metacognition is how well you know you're doing. Finally, the things that we can see are performance. So speed and accuracy or precision, reliability, how, consistent are you as in this case, a driver. And then you're receiving feedback, and are you able to incorporate that feedback? So it's an ill-defined construct. In order to make it more defined, there are some papers out there that have started to break up the concept of workload into different subcategories. So we, in this case, focused on the operator workload instead of the imposed workload. And Strayer, Watson, and Drews came up with this very simple framework that has visual, cognitive, and manual, which correspond to the NHTSA regulations for original equipment manufacturers. And you can see how different tasks might fail or succeed across imposing limits on visual, manual, and cognitive workload. For example, with texting, the cell phone requires high levels of all three components. You must use your hands or thumbs to write the text. You must use your eyes to determine if you're writing the information correctly, typing the information correctly. And you must use your brain to think about the message itself. So sending and receiving and reading text, high on all three. Hands-free systems eliminate visual and manual components of workload, but we may increase or underestimate the effects of cognitive workload and time on task when interacting with these types of technologies. So you end up with this trade-off where you're not sure, you're not breaking any of the regulations, you're keeping your eyes on the road, you're keeping your hands on the wheel, but you're working a lot harder or for a longer period of time on simple tasks. So how does the study apply in this context? Well, there are several different ways that modern vehicles are starting to, I would say, go astray or kind of make design choices that are changing the driving environment for the worse. For example, recently this Swedish magazine has talked about a short study they performed where physical buttons outperform touchscreens in new car tests and in new cars, which from a cognitive standpoint makes perfect sense in terms of learnability and memorability of locations, haptic feedback of buttons. It doesn't take your eyes off the road, so you are able to learn location of buttons, do the task, turn up the air conditioner, change the radio, because all of that is learnable. With the touchscreen, you can have infinite number of menus. You can have information clutter. With a button, you can't do as much. It's limiting, but it is also learnable, memorizable. So I've always been kind of interested in this space. One of the ways that I first got interested in doing this type of work is because I read a news article about two men who were playing a new mobile application game called Pokemon Go, and they both of them fell off a 100-foot cliff near the beach in Ventura County. They're both alive, they're okay. But they both made the same mistake of walking off of a cliff while using their mobile devices. So the fact that they were able to look at their phones, not be aware of a hazard, and walk off of a cliff is kind of startling, which was the impetus for trying to figure out in these types of scenarios, for example, the large diagonal 17-inch touchscreen in a Tesla, different mobile devices that people use while walking around every day, what are the features or aspects of these types of interactions that might influence people's ability to attend to different information. So in a brief study, I utilized smaller mobile devices, larger tablets, and then across two studies compared doing a foreground task, which I'll show you in a second, and a background task simultaneously. First, individually doing the foreground and then the background task, and then doing them together. I also created a third group, which was what we dubbed the phony tablet. The phony tablet having the same screen size as the small cell phone, but the weight and dimensions via a little 3D printed piece of plywood, weight and dimensions, so cardboard as well, or sorry, not cardboard, quarters taped to the back to kind of simulate the same feel and weight as the tablet. So we had the phone, the phony tablet, and the tablet itself. Foreground, there was a jittering ball in the foreground. They were made to hold the target, which is that circle, black circle, at the line of tape behind it, holding this tablet or phone. They had to maintain about a 45-degree angle without occluding the background screen. And then there was a change in the direction of the arrow. One was always pointing the wrong way. The others all agreed, and they had to speak into a microphone the position of that change, 1, 2, 3, or 4. In this case, 3. So we found the same type of performance in terms of error. People were pretty good at the foreground task. And then simultaneously, when doing the background task and the foreground task, the error of the jittering ball within the target circle was about the same in terms of pixels. However, in the background task, the response, the vocal response, was much slower to the tablet, and the phony tablet and the phone performed very similarly. So in terms of dual task cost, so single tasking subtracted from dual tasking, mean reaction times were just over 100 milliseconds to the background change to produce a vocal response with a phone or a phony tablet. And then they were larger with the tablet. So about 100 millisecond slowdown. Not a very big deal, but larger screens may not improve performance more than they hurt performance of a secondary task while dual tasking. 100 milliseconds only seems to matter when you are traveling at high speeds. So in this context, having a 17-inch diagonal touchscreen might actually be worse than having a smaller screen, even though general heuristic would be bigger is better. Other scenarios that we've worked with were collaborating with a company called Peloton, Peloton Technology, and their goal was fuel savings of a platooned tractor trailer by decreasing the following distance to the pilot driver. So in order to create fuel savings, you had to decrease the following distance of the rear vehicle beyond legal limits, and they had some technology to do that. So by decreasing this following distance, these two vehicles, the rear vehicle would connect wirelessly to the front vehicle, and then the front vehicle's acceleration would dictate the acceleration and deceleration of the secondary vehicle. The steering, however, was not controlled. So the secondary pilot would be staring at the back of this trailer and for, maybe hours on end, and they would have a very short following distance, and they would be maintaining the vehicle's lane position. So we know the general distances of perception and reaction and brake time in order to keep from hitting a vehicle. But with wireless connectivity, you can get rid of that time, and so the near simultaneously have brake responses to the rear vehicle and the forward vehicle. The issues that we discovered were, one, fatigue and boredom in the second driver who is, staring at the back of a vehicle, but also still having to maintain lane position. And then two, failures of the system, because all wireless communications can drop out. Failure of the system leads to the rear driver incapable of responding in time to any type of movement change in the forward vehicle. So they are still working on trying to create this fuel savings over so many million miles, vehicle miles traveled. It could potentially be billions of dollars. But the human component of the technology is the hurdle. So I talked a lot about some applications of how we might, of how people might be impaired in these different scenarios, but I didn't really talk about how we go about measuring their impairment in the first place. So here's one example of us measuring via a simple secondary task, the driver's workload.
I'm going to try out that DRT device really quick. So you'll be responding to the red light that appears in your peripheral vision by pressing the thumb button against the steering wheel.
Okay.
All right.
Siri, play the Beatles.
Call Chris Hunter.
Call Chris Hunter Mobile. Is that right?
Send it.
Sure thing. Sent.
Okay. So this seems kind of hacky, right? Like, why is this the best approach? Well, in assessing cognitive distraction in the automobile, Strayer and colleagues used a NASA task load index detection response task, which is the light, and also EEG P300 amplitude to try and explain brake reaction time and following distance. And the NASA task load index, which is a self-report survey that they do afterwards, actually explained the most, variance had the largest, explained the most of the effect size in partial eta squared of any of these tasks. So there are pros and cons to all of them, but it seems that P300 amplitude to the response and ERP with EEG and continuous measures are too noisy. Pupillometry has an issue on the road as well because of variable light levels. So actually on the road in vehicles, the best way to implement this is actually just to ask people how hard their driving was afterwards. But if you want to get fluctuations, real-time fluctuations, a good way of going about it is to have a secondary task, a highly automated secondary task, which is the detection response task. So is this the best approach? One answer is to have multiple measures. So you can do the detection response task and NASA task load index. It's very simple. You have like a light mounted on the head or a light mounted on the dashboard or a vibrotactile device. You can have multiple types of tasks. Maybe they have to press the button if the light is red, but not if it's green, something like that. Or they just have to press the button if they think they see a light. Easy stimulus response. When they're doing some sort of task like counting backwards by threes, then there is less resource available for them to respond, and their response times slow. However, you also produce a second event because you want to sample the environment continuously. In the International Standards Organization, DRT standards, you sample the environment randomly at a uniform distribution between 3 and 5 seconds. So if they don't respond by 3 seconds, they might have a second light coming up. So that is the upper limit of slowness, which causes another problem. They respond a certain number of times, and then occasionally they fail to respond, which results in misses. So then you end up with this second measure, which is hit rate. So you have reaction time and hit rate. Hit rate and reaction time cause a problem because it's a speed accuracy trade-off, which is hard to account for. One way to do it is to create a model that accounts for both, and we utilized evidence accumulation modeling. Evidence accumulation modeling is fairly simple. When you're interested in cognitive workload, you have some sort of start point at which point the stimulus appears, and then you accumulate evidence in mirroring neural processes, which reaches some response threshold. If you do that enough, you end up with a response time distribution, just like what the DRT releases. We've done quite a bit of work on how evidence accumulation modeling accounts for omissions and how it predicts workload. I'm not going to get into all of that, but it's fairly interesting, and it's actually a pretty good measure and works better than just comparisons of averages. We also use an operation span task, which is kind of the hammer, or the sledgehammer, that we compare everything to. So in this task, you have to respond to multiplication problems with true or false, and then you're either shown images or in an auditory operation span, read them out loud. Once you have memorized all of the objects or words, you have to then, at the end, repeat them back in order, and there's a scoring system. This is very difficult to do, and it forms kind of the thing that you should not do while driving ever. So this person's trying to think of what came first, and I believe they're actually getting it wrong. So that's a visual version. There's also auditory versions. So what do we do with these measures? Well, we can create standardized unit workload ratings. Single tasking can be normalized and anchored to 1, and then we can spread the distributions up to the operation span task at 5, and then see where relatively different types of tasks sit on this interaction. So listening to the radio versus a book on tape, slight differences. Interestingly, passenger handheld cell phone and hands-free cell phone are very similar in terms of their workload. However, it increases when trying to interact with speech-to-text systems. Okay, I'm going to skip over to some new types of tasks that we would be interested in, such as giving your car commands. Giving your car commands doesn't seem to be too bad. Listening to a natural recorded voice versus a synthetic voice seems to be fairly similar. Composing a natural voice versus having a synthetic pre-recorded composition are fairly similar. And then trying to interact with a high reliability menu, meaning selecting options from a menu via manually interacting, versus a menu with low reliability, meaning you make errors and you have to go back, are pretty high. And then finally, remember operation span task was up there around 5. Blood alcohol level of 0.08 is around, I think it's just under 3. Siri-based interactions, over 4 standard deviation units on our workload scale. So Siri is worse than being drunk. We tested several different types of vehicles, so Toyota, Hyundai, Chrysler, Ford, Mercedes, Chevy, on this kind of scale. And we did it across not only standardized measures of DRT reaction time, but also across the NASA task load survey for perceived workload, which has some subcomponents, but we collapsed across them to demonstrate interacting with, at that time, Chevy's system was producing the highest amount of workload. We also did some physiological measures, for example, heart rate, which was highly variable and not very predictive of anything. But but with some combined converging measures, we could standardize these types of scores to get some outcomes. Chevy doing the worst, Toyota's system doing the best. So Hyundai's Blue Link system led to an increase in workload from the Toyota system, a level which was similar to holding conversations over a cell phone or with a passenger. Music selection and call placement using Chrysler, Ford, and Mercedes seemed to lead to a level of workload similar to the error-free speech text-to-system that was evaluated earlier. Music selection and call placement using Chevy's MyLink system led to levels of workload that were greater than any other of the systems of interaction. So if any of you have used these systems, this is kind of how they stack up against each other. So we'll move on to actual applications, which are using DRTs on the non-driver and the driver to demonstrate cognitive workload fluctuations in real time, something that NASA Task Load Index can't do, of a conversation in the simulator. So how does the conversation with a passenger differ from conversations with hand-free cell phone systems in terms of workload? We figured, based on our previous tests, that drivers conversing with a passenger will have more control over voluntarily allocating their attention to the conversation or the driving task than drivers conversing on a hands-free cell phone system. However, we believe that the previous studies have demonstrated that cognitive workload measures are fairly similar in comparisons of means for conversations with a passenger versus conversations with a cell phone. So we had a remote group talking on the cell phone and a passenger group. One person performed a practice drive and then a baseline drive, and then they switched places. Person two performed the same practice drive and baseline drive. And then they had a natural conversation for 15 minutes, just kind of catching up, talking to each other, while simultaneously the entire time responding to our detection response task. We found that in terms of reaction time, something you'd expect to find is the driver had a slower reaction time than the non-driver. When the driver was talking, they had a higher workload in terms of slower reaction time than they did when they were listening to the passenger. And when they were talking on the phone and the non-driver was talking on the phone, the driver's workload was very similar. So that's kind of what we expected to see in our measures. When the passenger was talking, we had kind of a, when the non-driver's responses were the inverse. So lower workload when they were listening to the driver, a little bit higher when they were talking to the driver, and when they were talking on a phone, when they were listening on a phone, and when they were talking on a phone, the same pattern emerged. One thing that was interesting about this outcome is that when they were listening to the driver talking on the phone, the passenger's workload was fairly low. When they were listening to the driver talking in person, they had a slightly higher workload. One of our hypotheses about this type of interaction, and based on previous research, is that the passenger may be sharing the load of driving, thereby offsetting the load induced by conversation. The passenger has a vested interest in these types of interactions in the vehicle because they also don't want to get into an accident. And it's been demonstrated that people over the age of 16 who have their driver's licenses stop talking as much when driving environments become more difficult. We applied our model, evidence accumulation models, to this. All of those letters, B, V, SV, are all parameters and we allow them to vary all of these different parameters, B being threshold, V being rate of evidence accumulation, SV is its own parameter, variation in rate accumulation, and then the last one is T naught being non-decision time. We allow all those to vary, and then we hold one constant, and then we do model comparisons to see which parameters actually matter. We were interested in seeing if there was a difference between talking on a cell phone and talking to a passenger. And we found that the parameters accounting for listening versus talking mattered, so that a threshold accounted for driver talking to a passenger talking to a driver, and a non-driver with a cell phone talking to the driver. But a driver with a cell phone required a rate threshold and a rate parameter and a threshold parameter, neither being sufficient on their own to account for the driver's workload. So there was something special or interesting about talking on a phone that we are interested in exploring further. Finally, we held rate constant and threshold constant, and then simulated data to recreate our response time distributions. And when speaking with the passenger, threshold again accounting for all of the effect, and then with the cell phone user, threshold accounting for a decent amount of the effect, but rate was required in order to demonstrate the significant difference between talking and listening. So in terms of the parameters and how they map onto our cognitive concepts, we were thinking of the threshold parameter as being the ability to allocate allocate resources to one task or the other task, and threshold changes meaning that they're actually more successfully allocating resources while talking to a passenger versus talking on a cell phone, even though no mean differences existed. Finally, we looked into the time course, the scenario here being what amount of time is necessary to recover from doing some sort of dual tasking, for example, texting at a stoplight, but then stopping and going forward. We did it across 2 experiments, one a very simplified tracking task, and then 2 in a driving simulator. Similar type of setup, practice drive, baseline drive, and then counting backwards by 1s for 20 seconds, recovering, counting backwards by 3s for 20 seconds, and recovering. They did this 10 times. There was an easy drive and a hard drive. Both experiments had DRTs. Experiment 2 employed eye tracking, and both experiments found similar RT and hit rate curves. These are those curves. On tasking, blue counting backwards by 1s, red counting backwards by 3s. Reaction times are elevated above baseline when doing these cognitive tasks. And then there is a lag in recovery, meaning they're slower immediately after doing so, up to around, in this case, 18 to 21 seconds in the outcome. In hit rate, we saw a similar effect. It wasn't as big. In experiment 2, in the easy driving and the hard driving environment, there was very little difference, but we found very similar curves. And then finally, eye tracking found the exact same types of curves. So residual cost of multitasking can last up to 30 seconds after the secondary task has been completed. Physiological measures like pupil diameter also demonstrate the residual cost curve. At 60 miles per hour, you've traveled almost half a mile before returning to baseline cognitive workload. Long time to be driving impaired. So the characteristics of technology like screen size may have unexpected outcomes in dual task settings. Performance decrements from multitasking aren't solely caused by information processing. And then up to 30 seconds after stopping that secondary task in the car, you're still not driving as well as you were before that task. Thank you.
Wow, what an amazing talk. I learned so much, Spencer. This is incredible work, and thank you for bringing it to the citrus community. I'm sure if everyone was clapping on Zoom, it would be ruckus. We do have some questions from the audience, and I encourage you all, even if you don't have it perfectly formulated, please add your questions. The first one comes from Sam Padilla, a citrus intern and a psychology major at UC Merced. It seems that laws are not enough, and even though we know that distracted driving is a threat, as you showed, that we can't help ourselves. What policy measures to improve traffic safety do you think would help? And is it that we should all ride share and have a passenger help share the cognitive load?
Yeah, I mean that's the $1 million question, and the hardest challenge is that we have a strong cultural love of driving, and driving for many reasons is not the best, most efficient, best infrastructure, etc., for transporting large groups of people from one place to another or goods. So there's maybe some potential collaboration in terms of with policymakers and with other industries to try to shift cultural opinions towards alternative transportation measures. The like electric vehicles and automated vehicles are kind of band-aid solutions to our larger infrastructure issues in the US, and the idea of transport might have to be solved by people changing sociocultural aspects about our society. In terms of policies now, hands-free systems may get good enough to be different from handheld systems, but right now they're not. So we might have to start banning them from in original equipment manufacturers using them.
Wow. Yeah, it seems like one cultural change that might be easy is to introduce ourselves as I'm on the phone. My response times will be slower, but we still have that anticipated response, or we privilege the phone conversation over the and I wonder how we create that hierarchy.
Yeah, my advisor at Utah tested as an expert witness in criminal court cases, and in interacting with these people who've been in crashes, they said they couldn't help themselves from responding. You know, it's like a Pavlovian response interaction to the ding or whatever. So people started putting their phones in the trunk. So they would put their phone in the trunk for the drive, and then they wouldn't be tempted to interact. And the other thing that's great about some settings is automated messages that say, I can't talk right now, I'm driving. So if you send a text, you receive that text back, you know that person is currently unavailable. That kind of helps with the politeness of responses and the social pressure.
That's awesome. And full confession, I might have to put my phone in the trunk.
I mean, yeah, 10% of people any given daylight hour are texting or interacting. But you know, these newer vehicles with a lot of ADAS, driver assist systems, are trying to make up for driver distraction.
Great. I also wanted to reflect another question that Sam had. It is, why do you think that in an era of improved technology, car crashes seem to be ticking up? Dr. Camille Crittenden, our executive director at Citrus, looked up the data and said that recently it's been increasing since 2019. And I wonder if there's something with the convergence of cell phones and like our attention economy reaching apex and our belief that we can multitask at new heights, that there's some relationship there.
Yes, multitasking has been increasing. You know, it's early 2000s, I would say, when mobile devices started to become more commonplace. In 2016 or so, this talk had an intro that showed the trends per million vehicle miles traveled. Sorry. And that trend was increasing just recently. Had been falling since the fatalities. The fatalities had been falling since the advent of seatbelt laws across the different states, and then they slowly ticked up in the 2000s. But there was a drop off in like 2016 through 2018 that made it less convincing. So I dropped that slide. But pedestrian deaths are actually increasing as well, which is more difficult, which means that our automated systems for detecting hazards in the world are not good at detecting cyclists, pedestrians, etc. And that's where the real danger is.
Thank you. I do think we have time for one more question, and selfishly, as a kind of preview to your citrus work on wildfire evacuation, I was hoping you could talk about that. Citrus Seed Funds provided some of the research support for that, and I think Californians, between flood and fire, were trying to adapt and want to understand what might be a barrier for our success in any given situation. So thanks for giving a little highlight of that work.
Yes, sure. Let me really quick just share this slide. So this is kind of the framework that we're thinking about in terms of preparation. Is again the workload framework for evacuation decisions. And the issue with evacuation is time pressure. There's uncertainty about the information and trust and all of that. But also on top of it, time pressure causes overload, leading to panicked decisions. And panicked decisions are kind of an established term in fire science or fire safety science around evacuations. And one way of getting rid of those panic decisions is to spread that workload out over time, which requires preparation. Preparation not only in terms of what you can do in terms of packing, having lists, having a bug out bag or something like that, knowing your route and knowing where you're going to go, but also in terms of having experienced a fire situation before. So one of the ways we were looking at doing that would be to provide olfactory sense, smoke smells, haptic vest, heat, a VR system demonstrating fire, because it's really, really expensive to have everybody experience what it's like to be near or around fire in the large training facilities. And maybe these types of VR experiences, or even just watching videos of making choices while evacuating in some simplified types of games, might give people this preparation to make sure that they don't become overloaded. So that's kind of our approach. That's what we're working on, and moving forward, I think maybe we can contribute to some of the decisions being made during an evacuation in terms of route planning, driving, roadblocks, all of that.
That's wonderful. Maybe you can come back and do another seminar on your wildfire work. I'm blown away. I will never forget that Syria is worse than being drunk while driving. And I encourage you all to share this lecture with your most distracted driver friends. Maybe that's your own self. The recording will be available shortly on Citrus YouTube, and we hope to see you all next week for Dr. Michele Barbato's talk that's sure to be very interesting about hurricane risk and our dealing with climate change. Thank you so much, Spencer. I look forward to hearing more of your work soon.
Thank you for having me. I appreciate it.
Sure.